Hello, everyone. Today, I want to talk about making great apps, web apps and mobile apps, some of the problems that can make that hard, and a few of the patterns and solutions that I believe can help us build faster, more robust apps with less complex code that's easier to understand. For those of you who don't know me, my name is Byron, and I build technology and tools that help teams build great products. And I spent the last 10 years doing just that at Facebook, where I helped create a bunch of open source software that I'm super proud of, including React, Immutable.js, and GraphQL. But a couple of months ago, I actually left my job at Facebook, and I'm excited to share that I'm actually joining Robinhood to help lead web engineering there. They're driven by a mission that I really believe in, democratizing access to the American financial system. And they've got a ton of super interesting product and technical problems that they got to go solve. And they also use and contribute to a ton of open source projects, including the ones that my team at Facebook have been working on, like React, Immutable.js, Yarn, Flow, and a bunch of others. If any of that sounds exciting to you, don't hesitate to reach out. I'm trying to set up a whole new group of people at that place who are experts at the web. So I'm looking for more awesome people to help me on this next adventure. Well, I'm going to talk a little bit about some of the open source libraries that I've worked on. This talk is actually not about any specific library, framework, or platform. What I want to talk about today is the application architecture that applies just as much to native mobile apps as it does to web apps, and can be implemented in a huge variety of ways. But first, I want to get to a shared understanding of what we mean when we talk about architecture. Because when we're talking about software, architecture is a metaphor. We're drawing from the idea of building actual buildings, and there's some really clear parallels that we can draw. Architecture itself originates from studying one of the most important technological advances in building things, the arch. This very simple shape has proven to be nearly infinitely composable, allowing us to build larger and more complex buildings than were ever possible before. This is Vitruvius. He was a Roman architect and scholar, and over 2,000 years ago, he wrote about how good architecture should satisfy three principles: firmitas, utilitas, and venustas. Firmitas means durability. Vitruvius claimed that a building should be robust and have longevity. And when we build apps, we look for the architectural choices to do the same thing by reducing bugs and crashes, being resilient to future changes, all while maintaining good performance. Utilitas means utility. A building should be relevant to how it's going to be used. The materials, the technologies, and the aesthetics that you would choose for your own home would be super different from an office building or a house of worship or a conference space like this one, because each is going to be used in a totally different way. And similarly, the architectural choices that we choose for our apps are going to differ based on whether they're more static or dynamic, simple or complex, or whether they rely on more networked or live data. And finally, venustas means beauty. Buildings should use proportion, repetition, and scale to be both usable and desirable. And obviously we want our apps to be usable, but I actually think the parallel here is not to user experience, but to developer experience. The architectural choices that we make impact how easy or hard it is for our teams and ourselves to improve and iterate on our apps over time. So I think we see beauty in app architecture that makes future changes to our apps feel totally natural. So architecture is about making fundamental structural choices about how to build things with the same qualities that Vitruvius set out for us 2,000 years ago. And in software architecture, we make these same fundamental structural choices based on our understanding of what our app needs to do, the challenges it's going to face, and we choose our few elements, our abstractions, to create variation, robustness, to support the role of our app, to solve its primary challenges, and to create a productive space for developers. And for the information-rich, user-facing apps, like the web and mobile apps that a lot of us have been building, there's been a dominant architecture for the last few decades, MVC and REST. And for the kind of apps that we're building, the single biggest challenge that we need to solve is this: what changed? How can I tell when something has changed so that my models and my views and my servers can all stay up to date? And I really think that MVC left us with a poor solution to this problem because it attempts to solve it by adding even more things that change. Models send change events, views can really easily get out of sync, And servers can quickly get race conditions or tricky to handle failures. Because when models and views both need to listen to each other for change updates, it's easy for what seems like a small change of updating a model to actually have these cascading and unpredictable effects on your whole application. And this gets even more challenging when we consider that models and views are often nested and hierarchical. And there's actually a second big challenge that information-rich apps face, and that's synchronizing data with the server. So modern mobile networks are just super crappy, right? First there's latency. In the worst case scenario, we can measure latency in whole seconds, so minimizing the number of requests that we send is pretty critical. And then there's intermittency. We often talk about, in web apps in particular, supporting offline mode, but really what we're talking about is just walked underground mode or driving between cell towers mode. So really what we want is the ability to handle network failures, and that's going to be critical. And so while REST helped us model our data in terms of a networked service, it can kind of be crippling to performance when our app needs to load data that's dependent on loading other data. So for example, say we wanted to build a social calendar app. First, we'd get our friends, we'd get their names and their avatars, the next events that they were going to attend, and the details and names of those events. And since REST APIs typically return URLs to load when one resource references another, we could actually end up loading a ton of URLs to render our application, some of which we can't start requesting until the previous URLs have loaded. And when network latency on mobile connections is measured in big chunks of a second, this can add up pretty quickly and result in a slow experience. So we need to deal with the problem of having both a flaky network and a slow network. And that puts us in a really sticky situation. Because since networks can be flaky, we might want to show a loading indicator and be conservative, so when the user performs some action, they know that we're working to make sure that that happens. But networks can be slow, so we might not want to make them sit around and wait all the time. It might just be better if we just pretend the action worked. But what if it doesn't work? What if we have to change the UI back to what it looked like before? And what if they've already done some other action before we hear back from the server or get some failure? These are all challenging and unfortunately really common scenarios that we have to deal with in the apps that we're building. And I actually think there's a really powerful technique that we have to get a better handle on tracking what's changed, and that's by tightly controlling what can change in the first place by embracing immutability. Immutability means that we never change things in place. Instead, when we want to reflect some update, we actually create a copy with our change applied. And what's really exciting to me about this is that immutability isn't more complicated than what we've already been doing. It's actually simpler because we've removed the feature of being able to edit things in place. Of course, when we give up the ability to mutate our data, we're giving up some of the power and abilities that come with that. But in exchange, we actually get new principles, new guarantees about what can and can't happen in our programs. And I actually think that this is at the crux of choosing the right coding languages and tools. We balance between power and principles. Because if we only cared about writing code with the most power, we would have stopped at assembly and goto. You can literally do anything with goto. It's super powerful. But instead, we're constantly looking for more principled application of the power that we already have. So we forgo goto and we embrace for loops. You can't do everything with a for loop that you can do with goto, but the principles and constraints that it provides, it gives you some guarantees about what can and can't happen in your software, and then you can leverage those guarantees. And some languages actually omit for loops in favor of list comprehensions like map, filter, and reduce. Again, less power in exchange for more principles, more guarantees. So I think it's not about the power in your code, it's about the principles that you can leverage. And immutable data brings with it principles, guarantees, that we can leverage to use techniques that we couldn't safely rely on before, like memoization and cheap undos or rollbacks. And there's another really powerful technique we have for producing highly leveraged principles, and that's using declarative abstractions. Declarative means that we write code that explains what we want rather than how we want it to be done. And that lets us get much smarter about how to be organized about how that how actually happens. And it usually happens at a lower layer, usually in some library code that you don't have to deal with. So I'm kind of done with MVC and REST, and I think it's time that we rethink how we architect our apps. And as I've been observing apps built both at Facebook and in the larger developer community, I'm starting to see a new application architecture emerge to better solve these problems. And I don't know if it has a name yet, so I've started to call it the Immutable Declarative Executable Architecture, or at least that's the idea I came up with. And it's heavily inspired by similar architectures that you might find in functional reactive programming environments like Elm. And now, this doesn't mean that our UI is going to be frozen and we can't interact with it. Instead, what it means is that we're going to embrace the principle of immutability and declarativeness throughout our app so we can control exactly where change occurs. And that means that it's going to be a lot easier to actually track what changes, and we can take advantage of techniques like Memoization to keep our app snappy and up to date, and then cheap undos and rollbacks to make sure we can handle failure gracefully. But first, let's start with first principles, stuff that we all know, views. Every platform that we care about for building apps, they already have a native concept of a view. We don't have to reinvent this wheel. The web has the DOM, iOS has UI views, Android has Android.view, et cetera, But all of these basically have a similar API where you build up a view tree. We want to use these views because they expose the native user interface on every platform, but the APIs kind of suck. You create elements, alter their properties, and then add them to parent elements. All of these are mutative operations. And then you have a bunch of references that you need to mutate over time and keep track of those references. All of this makes it really hard to implement the kind of optimizations that we need for drawing fast UIs like minimal updates and view recycling. So what we really want is an abstraction on top of views that lets us declare what views should be displayed at any point in time. Of course, we all know this, we call it components. And a component is just this pure function. The current state of the world goes in, and a representation of what we want on the screen comes out. We all know this as the render function. But what a good component library should do is provide this pure functional developer API, but then under the hood, provide the highly optimized management of the mutable views underneath. That how? By updating only exactly what needs to be updated and recycling views when our component function is called a second time. Components are a really important aspect of this architecture, and obviously React popularized this concept. We all know this. React lets us write pure JavaScript functions, and then it manages the mutable DOM elements for us. And we know React Native as well. Again, JavaScript component functions, but actually managing the native UI views, Android views, Windows views, and all of the other various platforms that React Native has been ported to. But this isn't a JavaScript concept at all. I think this is a higher level concept that can lend itself to any environment where we're drawing UIs. And we've already done that. So there's pure native implementations of components as well. There's Component Kit. That's an all Objective-C implementation of the same idea for native iOS apps. And then there's Litho, which is for all native Android apps. And if you've ever used Facebook's newsfeed in either iOS or Android, then you've seen Component Kit and Litho in action. And these component functions, they need to take some data as input, and that's where models come in. But these are not your typical bloated model classes with tons of methods and change event emitters. These are, of course, immutable models. And I often recommend implementing these as just plain old objects, data getters only, or persistent data, persistent immutable data structures, like the ones that Immutable.js provides. But basically, models are data, and that's it, nothing more. And I think that these two concepts are tightly coupled together, and we have to recognize this. Components render data from models. So when a component wants to render something new, the corresponding model that it renders needs to include that data as well. But that poses some problems because a model is often used in a lot of views, and it's typically defined in different parts of your code base in a different file. It's pretty easy to accidentally forget to include something in a model, and then you get a broken UI. Or if a view no longer needs some data, you forget to remove it from the model, and then you end up loading and passing around all this unused data that's just slowing down your app. So this is tricky enough to solve with a single app runtime, but modern apps also have to talk to a server. So not only are apps and APIs often written in different languages and held in different code bases, they also have different life cycles and are deployed at different times and typically have different people working on them. People might be using an older version of our app, which might expect different versions of our models that our current version of our API provides. There's just a whole wealth of problems to solve here. And to help solve these sort of problems, we built GraphQL. GraphQL is a declarative application-level query language for APIs. And this is what it looks like. This is the hello world of GraphQL queries. This is how I query my name, if for some reason I forgot it. And the first thing you notice is it looks kind of like JSON. That's intentional. There's these curly brace things that look a little bit like objects. We call them selections. And then inside that, you see some things that look a little bit like object keys. We call those fields. And fields can have sub-selections, which allows us to describe sort of deeply nested requests. And if we send this to a server, we get back this executed response. And you can see that the response and the query have exactly the same structure. And this is one of the most powerful principles, the guarantees, in GraphQL. In GraphQL, queries describe the shape of the resulting data. So because of this, you can actually usually work backwards from the data that you want to see in your app and get the right query. So let's test that out with an example. That social calendar app that we talked about before. We expected to get our friends and the names and avatars of those friends and the next events that they're attending and then the details of those events. If we wanted to write a GraphQL query for this, it basically writes itself. And remember that that query can be sent in a single round trip to the server, typically replacing many related REST requests that depend on each other. So the reduced latency can add up in some pretty significant load time savings, and less trips over the network means less opportunities for failure. And GraphQL also has a unit of composition, similar to functions in a programming language, called fragments. GraphQL fragments are useful for describing and reusing specific bits of data requirements, but I think most importantly, what it does is it lends itself to that tight coupling between models and components. So each fragment here corresponds directly to a UI component in our app. Social calendar represents this whole list, that avatar is just the name in the picture, and then the calendar synopsis is just those few events. And so this structure makes it really easy to add or change our UI and make sure that we know exactly what data is going to be loaded in for each part of that. So while conceptually our models might describe all the data that would exist, what we really actually care about is just the data that's used in a particular render function. So if each component declared not just how to render a model into a view, but also declared exactly what data that it needed, then we could actually work backwards to determine all the data that our whole application needs from the server, and then we could automatically generate the code from our queries and models that we used to have to write by hand. Again, we can do this because it's declarative, so we don't have to worry about the how, and we can leave that up to sophisticated software to solve for us. Because the data that you need is declared right next to where it's rendered, it's way easier to see if you're asking for more or less data than you actually need, which helps stop both that overfetching and underfetching problem. So at Facebook, we coined this co-located data dependencies. But the basic idea is that you put your data requirements for any component right next to its render function. And this pattern was originally popularized by Relay, but now it's actually used in a bunch of different frameworks, and not just in JavaScript, in a bunch of different platforms as well. So this is good, but what we have so far is good for read-only apps, like maybe a news reader. But what about apps where things change? We also need to represent actions, which can result from when a user interacts with our views. And actions need to be able to perform some changes, and since we might have a whole bunch of models that are all immutable, we need one place where we can apply those changes, and that's our app state. State's where we keep the most recent version of all of our models, and it's where we apply our actions, and it's also where we put the result of that very first query to our server. And of course, we want our app state to be immutable too, so what exactly happens here? What does an action look like, and how do we actually update this thing? Well, let's take a closer look at an action. It's just a function. It's a function that takes in the old state of the world and returns the new state of the world. That might mean that you might make a new version of a model with some change applied and then return a new state referencing that new model. And if you've used Redux before, then this isn't new to you, right? This is just states and actions from Redux. And so once an action returns a new state with some new models, then we can provide those to our components again, which are going to describe our new views, which efficiently updates the underlying native views, and then we can interact with those updated views to get a new action, and you can see that this is just going to be a never-ending loop. And so some of you might be thinking, a new state for every action, that's going to be slow. You said you're going to have to copy things instead of updating things. it's not actually slow. There's some really cool techniques that we can use to make this really fast. And the most interesting one is called structural sharing. And this is what allows us to maintain both immutability and great performance. So when we make a copy of our immutable structure to apply some change, we're going to do that based on some original copy, and we're going to literally share as much of that previous structure as possible and the underlying memory as well. And we can use this technique manually for just plain objects and arrays, but it's actually the basis for an entire family of super interesting data structures called persistent immutable data structures that you can actually use to replace the native mutable arrays and objects and maps. And I built a library a couple years ago, which some of you might have heard of, called Immutable.js. It provides these data structures and some APIs for working with them. But you can actually find persistent immutable data structures in a bunch of other environments. In fact, they're actually the default out-of-the-box data structures that you use in a lot of really popular functional programming languages like Clojure or Scala. And by the way, Immutable.js is getting a lot of my focus these days as we're ramping up to a v4 release, and it's something that's like heavily used within Robinhood, so it's something I'm super excited about. So let's see what this concept of structural sharing looks like in action. Let's say we want to make a change to just this one bit of data in this whole structure. Well, it's immutable, so we can't just edit that in place. Instead, we're going to make a copy of that piece of data with that edit applied, and it can still reference other pieces of data that haven't changed, and we know that's safe because they're immutable. They're not going to change out from under its feet. And then anything that pointed to that old node needs to point to the new one with the edit applied, but again, no mutating, so new copy with the edit applied. And then we just repeat this until we get to the top of our structure. And then here's our whole new structure with our edit made. And you can see that the old and the new structures, they actually share most of the same memory. More than half of this is shared, and this is a super basic example I made just to fit on the screen. In practice, you get upwards of 95% of memory sharing between those various versions. And most importantly, this previous structure was left completely unchanged. It's persisted in its immutability. And because of that, we can actually use both the old and the new structure at the same time, which is part of what allows us to do easy undos and rollbacks in the case of failure. And if we no longer need to hold on to that, then we can just let it be garbage collected. And in good environments with good garbage collectors, like basically all modern JavaScript VMs, this is super fast. So by using structural sharing in our models and in our state, we can ensure immutability without serious sacrifice of either CPU or memory performance. And of course, immutable data does have some modest overhead versus the direct mutation of memory, but that's often more than offset by some of the global performance optimization techniques that it enables. And I think the most interesting one is memoization. So memoization is when you call a function and it checks its arguments, and if the arguments are the same as the last time you called that function, then it just returns what that function returned last time and doesn't bother recomputing anything. And that's really useful for expensive functions like, for example, rendering your whole application, right? Or at least rendering big chunks of it. But that really wouldn't be possible if the arguments going into that function could just kind of change under the hood at any point in time. Then it would no longer be safe to rely on, same arguments in, same value out. We actually need immutable data in order to make memoization possible and fast. So coming back to our diagram, we're still missing a really important part here, and that's how our actions communicate with our server. So let's go back for a second and look at what that action was. So if an action needs to talk to our server, we're going to need to wait for our server to respond, which might take some time. So we can't really say that we're going to return a new state right away. We have to be asynchronous, so we're just going to promise that we're eventually going to return a new state. But waiting sucks, right? Like even in the best case scenario where our server is really fast, we humans can perceive delays in just hundredths of a second. So even if our server is super fast, we're on a really fast connection, it's still going to be noticeable. But if we're waiting on a typical slow mobile connection, this could actually be downright painful. So what we really want is two things. Both instantly providing a new version of our state that's like an optimistic guess at what we think the server is going to return back, as well as that promise for the real update from the server. Which brings me to one last problem. What happens when we're performing multiple actions at the same time? For this, we need a queue. The queue holds on to all the actions that are currently in flight, and it ensures that they always apply to the app state in the right order. And actually think that there's some pretty awesome libraries out there for all the various pieces of this that I've talked about, but I couldn't find a lot of good examples of queues for actions that are out there, so I think this is a good opportunity for people to build new things. And I realize that there's a ton of super interesting and really deep content, a bunch of different approaches on how to deal with distributed synchronization and managing race conditions, but I only have a few minutes, so I just want to illustrate one such strategy of how a queue can work. So my queue keeps track of the most recent true state, which is what the server told us that it knows. And then when an action happens in our app, we're going to put it in the queue and then immediately derive an optimistic state. So that's going to give us immediate feedback to our users. And then if another action shows up before that first one's done, that's totally okay. We just add that to the queue and again, immediately derive a new optimistic version of our state. And so if we're underground or on a spotty connection, we can just keep using our app and keep making more actions, and we'll see effects immediately, and this action queue will just continue to grow. And then once the network returns, the actions can send their data to the server, and we can remain up to sync. So when that first action finally finishes and we get the official update back to the server, then we have the new true state. That action can be removed from our queue, and we can compute a new optimistic state by replaying any remaining actions we still have in the queue. And then once all the actions in the queue are completed, the queue is empty, and we're back to displaying only true data according to our server. So if an action ever fails, we can simply replay all the actions from the last known good state after doing one of those cheap rollbacks to a state that we knew was good. There's lots of opportunities here to do really interesting things depending on what your application needs. So let's take one last look at this whole architecture. Our components describe the data that they need, which informs the shape of plain old object immutable models, which are first created by the result of a declarative GraphQL query to our server, creating our app's initial state. These models are then provided to our components render function, which describes the views, which are actually created in the underlying native UI framework. We can then interact with those views to create actions, and those actions are going to optimistically create new versions of our state immediately, but also add it to a queue to asynchronously let the server know about that change. When the server responds, we can take the action out of a queue and then provide a more accurate version of our state, which contains new models, which are again provided to our component function, which again describes our new views, which we can then use to apply a minimal set of changes to the existing underlying UI framework. And this goes on in a loop. So I think that this makes some dramatic progress on solving some of the challenges that we face. Keeping track of what changed, keeping the UI up to date, and synchronizing with the server that's typically on the other end of a spotty and slow network connection. And we can do this precisely because everything is immutable and declarative. If any part of our code base could edit our models or store at any time, which is really common in MVC frameworks, then we couldn't use these techniques anymore. We couldn't know when to render a component to get an updated view or optimize rendering those views. We couldn't reapply actions in order or easily roll back to a last known good state to handle failure conditions or intermittency. And on multi-threaded platforms like iOS and Android, we couldn't take advantage of performing work off main threads for fear that something would get mutated and we'd end up crashing. And I think that this architecture is actually more simple because there's no direct mutation. And I know that I've gone into a lot of depth on all the various pieces here, and indeed, libraries like GraphQL and React can be pretty sophisticated under the hood, but they can be that way because they're built atop simple principles: pure functions, immutability, and composition. And I'm really excited about this architecture because I've seen it work really well for building apps, both simple and complicated, especially super complicated apps at Facebook like Newsfeed. Our mobile apps largely follow this architecture. And I believe that this is directionally where app development is headed, and that both traditional MVC and mutation by default are going to begin to fade into the pile of old ideas. But I want to leave you with this. While MVC and REST didn't solve all of our problems in app development, what I've presented today also will not. These ideas are far from flawless, and I want us to all continue to challenge the notion that there's ever one right way to make things. Because let's recognize just how quickly and continuously our ideas of architectural quality change and improve. Just about every time I finish building something, I just have this deep urge to completely start over, because by the time I'm done, I can see a better way to do it. But of course, if I were to rebuild all my projects, as soon as I'd finished the rebuild, I would have seen another great way to do it all over again, and I'd just get stuck. And I think software architecture, it suffers from this idea from psychology called the hedonic treadmill. We're constantly looking ahead and trying to find the perfect answer to all of our problems, and then we complain about every bump in the way. JavaScript fatigue. But this process of architectural improvement, it's actually never ending. There will always be trade-offs. There will always be new problems, and there will always be new ideas. And we just simply never will arrive at a perfect software architecture nirvana. And for me, this was a really important emotional realization, because to love what we do is to love the process of improvement itself, rather than seeking some mythical destination of being perfect. So I hope that you find the idea architecture useful for what you're building today, but more importantly, I hope it inspires you to continue to improve upon the ideas that we have here, challenge the way that we're building things, and rebuild established best practices so that we can all build even better apps tomorrow. Thanks, everyone.